Yeah, in this video, I'm going to discuss about the Sugdens single electron concept, Sidgwicks maximum covalency rule, and Sidgwicks Powell theory. Yeah, in my previous video, I've already discussed about the Lewis theory and its limitations. Yes, and before going to the theories, let's look at a quick recap of what is this octet rule and what are the limitations of this octet rule. This octet rule says that the molecules or the atoms try to attain the stability by either by means of ionic bond or by means of covalent bond, by means of ionic or covalent bond, by attaining the 8 electrons in its outermost shell, that is its valence shell, by means of sharing or by means of the transfer of the electrons from one atom to the another. By attaining this 8 electrons in its outermost shell, it tries to attain the nearest noble gas configuration. So we know that these noble gases or the inert gases in the periodic table are the most stable. So these atoms or ions will try to attain this 8 electrons by means of which it can attain the nearest noble gas configuration. So the main concept of this octet rule is 8 electrons in the valence shell. But there is certain limitations to this octet rule. So what are those limitations are? It could not explain the stability of the molecules with incomplete octet. For example, if we take this boron trifluoride or BeCl2, in the central atom of Bf3, that is boron, it has 6 electrons. And for this beryllium, it has 4 electrons. So even though it has 4 and 6 electrons in the central atom of these particular compounds, that means they're having less than 8 electrons, these two, even though they're having less number of electrons in the center atom, they are stable and do exist. So Lewis theory or octet rule is unable to explain the stability of such molecules. And they are unable to explain the stability of the molecules with expanded octet. For example, if we take this PCl5 or SF6, for PCl5, the central atom has 10 electrons, and for SF6, it has 12 electrons. So even though they have 10 and 12 electrons in the central atom or valence shell of the central atoms, they do exist and are stable. This is what is the expanded octet, that is more than 8 electrons. And they are unable to explain the stability of odd electron species like NO and NO2, where the central atom, the nitrogen, has 7 electrons, and here it has 11 electrons in this particular case of nitrogen dioxide. These are also stable and do exist, and which could not be explained by the octet rule. And the octet rule does not give any idea about the shape of the molecules. So in order to overcome these limitations, few theories have been put forward which can explain the deviations from this octet rule. The first one is the certain single electron concept. The second one is Sidgwicks maximum covalency rule, and third one is Sidgwicks Powell theory. So the first one, let's look at this. What is that? Certain single electron concept. The first thing he said is the maximum number of electrons the valence shell of an atom or a molecule can contain is only 8. So it cannot exceed more than 8. So this is following the octet rule. Okay. But how could it explain the uh, hypervalent atoms, I mean molecules like SF6? We know that SF6, according to we have the structure of SF6 like this, where S is bonded to 6 other fluorine atoms by means of covalent bonds. According to this, the sulfur should have 12 electrons. So what Sugden said is, he said that it will form 2 covalent bonds with fluorine, 2 fluorines. That means 2 covalent bonds means 4 electrons. So how many electrons it is short of now to attain the 8 electrons? Only 4 electrons, right? So plus 4. So these 4 electrons it will attain by means of these singlet linkages. So the singlet linkages with other 4 fluorine atoms here. So in order to attain 8 electrons in its valence shell, the sulfur is forming 2 covalent bonds with 2 fluorine atoms and 4 singlet linkages with 4 other fluorine atoms, where it is sharing only 1 electron by means of this singlet linkage. So this singlet linkage or singlet is also called a single electron bond because it is sharing only 1 electron by means of this singlet linkage. By means of this single electron bond, it is sharing only 1 electron with other atoms. So this singlet linkage is being represented by means of this dotted line arrow or by means of singly this half-headed arrow. So yeah, when we come again, so what type of atoms are forming these singlet linkages are, if you observe here, here is a fluorine. So the electronic configuration of fluorine is atomic number is 9, so 2 and 7. So this is short of only 1 electron in order to attain the noble gas configuration, that is of neon, right? So such type of atoms which are short of only 1 electron to attain the noble gas configuration or the octet configuration will participate in this singlet linkages or single electron bonds. So this is what the Sugdens single electron concept says. So let us understand this theory by means of few examples. Like first thing is SF6. We have already discussed about this, where sulfur here, it has 6 valence electrons. So it is forming 2 covalent bonds now with 2 fluorine atoms. So 4 electrons it attains now. Now it is forming 4 singlet linkages with 4 other chlorine bonds by means of single electron bonds. So 1, 2, 3, 4, 5, 6, 7, and 8. So now this is sulfur is having 8 electrons in its valence shell. When we come to PCl5, the same here again. This phosphorus is forming 3 covalent bonds. So it is 6 electrons, so short of 2 more electrons. So 2 singlet linkages with 2 other chlorine atoms here. So total of 6 plus 2, it is 8 electrons in the valence shell of phosphorus. So now this chlorine, it's short of only 1 electron. See, this is electronic configuration is atomic number is 17. So 2, 8, and 7. So outermost configuration is 7, only short of 1 electron in attain the 8 electrons, that is octet rule. Yeah. Now this is how we explain the electronic, the structures of PCl5 and SF6. Now in order to calculate the number of the singlet linkages a molecule, atom can form, can be calculated by means of simple formula. He said that the number of singlet bonds is equal to the number of valence electrons minus the number of the electrons required to complete the octet. For example, when you are taking this SF6 again, this sulfur, so the number of valence electrons in sulfur is 6, S16, right? So it is 2, 8, and 6. So 6 valence electrons. So it is short of only 2 electrons in order to complete the octet. So it's forming 4 singlet linkages. So 2 covalent bonds, 1 and 2. So 2 covalent bonds. And 1, 2, 3, 4. 4 singlet linkages here, singlet bonds. And when we come to this PCl5, this phosphorus is 15 here. So it is 2, 8, and 5. So valence electrons are 5 here. So 5 minus, it is short of 3 electrons in order to attain the octet configuration. So 5 minus 3 is 2. So it is forming 3 covalent bonds, 1, 2, and 3, and 2 singlet linkages. So the total number of valence electrons here is 1, 2, 3, 4, 5, 6, 7, and 8. So phosphorus is having 8 electrons in its outermost shell now. Yeah. Let us look at a few more examples here. Let's take this IF7. So IF7, so the valence, so number of singlet linkages is iodine can form is iodine is a halogen, so the number of valence electrons is 7 here, so it's short of only 1 electron, so 6 singlet linkages. So it can be represented as follows: 1 covalent bond with 1 fluorine, and rest all are singlet linkages here, shown by means of dotted arrow here. All fluorines, a single electron bonds, only one covalent bond here. So 1, 2, 3, 4, 5, 6, 7, and 8. So one covalent bond and 6 singlet linkages or singlets or single electron bonds. And when we come to XeFO4, not F4, so Xe is forming all singlet linkages, only all the 8 singlet linkages with xenon, I mean with oxygen. So one electron bonds all this. So it's an inert, yeah, Xe is having 8 singlet linkages here. Yes, and the next theory which has been put forward in order to explain the limitations of octet rule is Sidgwicks maximum covalency rule. So what does this rule say? This rule says that the maximum covalency of an element is limited according to its period in the periodic table. So depending upon the period to which the element belongs, the covalency is dependent upon. So the covalency is nothing but the number of bonds an element can form. So it's the number of bonds that particular element can be formed. So it depends upon the position of that particular element in the periodic table. If it belongs to a first period, that means only hydrogen here, it can have only a maximum covalency of 1. That means it can have only 2 electrons in this valence shell. If it belongs to the second period, that is from lithium to fluorine, then the maximum covalency which we can expect is 4, and the number of valence electrons will be 8 then. And if the element belongs to third and fourth period, that is from sodium to bromine, then we can expect 7 covalency, and the number of electrons, that means in its outermost shell, will be 14. And from rubidium onwards, it is, that means from fifth period onwards, we can expect the maximum covalency of 8 and not more than that. So we can have the covalency less than what is written here, but not more than what is been written here. So for hydrogen, we can have only the covalency of 1, but not more than that. Yes, let us understand with the help of the few examples here. Uh, yes, when we take, for example, BeCl2, so its structure is this thing. So the beryllium is from second period here. Yes. So second period. So the maximum covalency we can expect is 4, right? So maximum covalency we can expect is 4. So but covalency we are observing here is only 2. So the molecule can exist. And when we come to BCl4 minus 2, that is, it can form 4 bonds with 4 chlorines. So the covalency here is 4. The maximum covalency according to this period number is 4. So this molecule can also exist. When we come to PCl5, it is phosphorus is third period element. So the maximum covalency we can expect is 7 here, right? Yeah. And what we are observing in phosphorus pentachloride is 5. So this molecule can also exist according to the Sidgwicks maximum covalency rule. But when you take the example of NCl5, nitrogen is again second period element, right? Second period element. So according to this, the maximum covalency we can expect is only 4. But now we can see in this particular molecule or compound, it is 5. So this molecule cannot exist because it is exhibiting the covalency of 4, where it can where we can expect a covalency of only 4, but it is in this particular compound it is exhibiting 5 here. So the molecule here does not exist here. So the main application of the Sidgwicks maximum covalency rule is we can say whether the particular molecule, the given molecule, will exist or not, is stable or not. So this is the main application of Sidgwicks maximum covalency rule. And the next one is the Sidgwicks Powell theory, where in 1940 this rule has been proposed in order to explain the shapes of the molecules. So to a certain extent, he could explain the shapes of the molecules. So what this theory says this so depending upon the number of the electron pairs in the outermost shell or the valence shell of an atom or a molecule, so depending upon the number of the valence electrons, we can predict the shape of the molecules, and the shape of the molecules with only sigma bonds could be explained, and the molecules with having pi bonds could not be explained. Means the shape of the molecules with only sigma bonds, he could explain them. So according to him, the outermost shell or the valence shell of the element or the atom contains the lone pair of electrons along with the bond pair of electrons. So he said that the lone pairs and the bond pairs of electrons, he considered them to be equivalent, since both of them occupy some space in the molecule, and both this there is a repulsion in between these lone pairs and bond pairs of electrons. So yeah, here it is clear. He said that there is the electrons which are present in the valence shell of the atom, they may be lone pairs or bond pairs, and there's a repulsion in between them, and they are considered to be equivalent, and they're considered to be occupying some space in the molecule, and they repel each other. So the repulsions can be minimized if they are arranged in such a way that they are farther apart from each other. So according to the number of the electron pairs in the valence shell, he arrived at the shape of the molecule. So if the number of the electron pairs in the valence shell is 2, if there are 2 pairs of electrons, he said that the molecule is linear. That means the bond angle is 180 degrees. And if there are 3 pairs of electrons in the valence shell, then it's trigonal planar, and the bond angle is 120 degrees here. And if it is 4 pairs of electrons in the valence shell, the shape is, for example, it is CH4 here, tetrahedral, and the bond angle is 109.28. And if there are 5 pairs, shape is trigonal bipyramidal, and the angle, so 3 atoms are arranged in one plane, and the 2 other atoms are arranged above and below the plane of the other molecule. That means there are 3 atoms are arranged in one plane, and 2 atoms are arranged above and below the plane of the molecule. Yeah, this is 120 degrees, and this is 90 degrees here. The 2 angles with bond angles we can see, we can observe in this particular case. And if there are 6 pairs in the outermost shell, then the shape of the molecule is octahedron, and the bond angle is 90 degrees. And if there are 7 pairs, then the molecule shape is pentagonal bipyramidal, where 5 atoms are arranged in one plane and 2 other atoms are arranged above and below the plane of the molecule, where the bond angles here is 72 degrees and here it is 90 degrees. Yes. So certain limitations of this octet rule or Lewis theory could be explained based on the other theories like Sugdens theory, that is Sugdens single electron concept, and Sidgwicks maximum covalency rule, and Sidgwicks Powell theory. And there are other theories also put forward, which I could explain in my next video.